Hello everybody, welcome back to Introduction to Oceanography. Today we are taking a look at Lecture 4 from Chapter 4 of our textbook, and this particular chapter is on ocean basins. And ocean basins will be an extension of everything we learned in Chapter 3 on plate tectonics, where the unifying theory of plate tectonics explains how ocean basins came to be, why they're shaped the way they are, why they have the features they do, and why they act the way they do. So we'll talk a little bit more about plate tectonics and then develop a better understanding of ocean basins. First, we're going to take a look at the overarching concepts that we'll be talking about in Chapter 4. So on to Chapter 4 main concepts. Number 1, tectonics shaped the seabed. We've already mentioned that. Tectonic forces, the unifying theory of plate tectonics, explains the shape of the seabed. The ocean floor is divided into two parts, the continental margins and the deep ocean basins. And those continental margins really are just seaward extensions of the continents, and they usually are granitic. They're made of granite. And the deep seabeds are completely different features, and they are made up of basalt, a low silica rock. Continental margins can be active with earthquakes and volcanoes, or passive, depending on local plate movement. The mid-ocean ridge system is perhaps Earth's most prominent feature. It's the world's longest mountain range. Most of the water of the world ocean circulates through the hot oceanic crust in these ridges about every 10 million years. Using remote sensing methods, oceanographers have mapped the world ocean in amazing detail. That's something we'll take a look at. All right, Chapter 3 in review. The Earth's crust is attached to the very uppermost part of the mantle, the rigid part of the mantle, into what are known as lithospheric plates. And what you're looking at here are those lithospheric plates broken down into all the different plates that exist on Earth's surface. We have the large Pacific plate and the North American plate, the South American plate, the African plate, which is composed of part oceanic and continental crust and lithosphere, the Indian Australian plate, the Eurasian plate. All these plates are moving along, they are rigid, and they're moving along on a hot and pliable upper mantle known as the asthenosphere. Some of these plates run into each other and they converge. Oceanic plates can converge. Oceanic and continental plates can converge. Continental plates can both converge. They also diverge, as we see at the mid-ocean or the mid-Atlantic ridge. They move apart, and they also have transform boundaries like we see in the San Andreas Fault. And of course those convergent boundaries, the Nazca Plate, where the Nazca Plate converges with and subducts under the South American Plate. So here are the basic plate boundaries and some of the different characteristics of those plate boundaries, much of which we have discussed in detail in Chapter 3. And if you need an update on that, I suggest you watch Chapter 3 and get more information on the divergent, convergent, and transform plate boundaries. One of the things that we learn in Chapter 4 is that we know a tremendous amount about the ocean basins by the mapping of ocean basins. And the mapping of ocean basins is the scientific pursuit called bathymetry. Bathymetry is the discovery and the study of ocean floor contours. And early studies often used just a weighted line, and they would just measure the depth to the ocean floor. Big advances came with echo sounding, and then multi-beam echo sounders, and of course finally with satellite altimetry. And we've seen these pictures from Chapter 1, different types of echo sounding, using methods of pinging through the ocean, sending a ping of sound and listening for it to bounce back and getting an idea of just how deep that particular part of the ocean floor is. And this is a very important advancement in understanding what the deep ocean basins look like. Multi-beam echo sounders provide more accurate measurements than just normal echo sounders. They use up to 121 beams to measure the contours of the ocean floor. They also get it done much more quickly. Satellite altimetry, this is kind of amazing. Satellites can measure the sea surface height from orbit, meaning they can see just how high the sea surface is from orbit. And what satellites tell us is that the sea surface isn't flat. Now you pour a little bit of water out on a table and it creates a completely flat surface. But what we know about the sea is that sea surface is not completely flat. Large pieces of crust, like a seamount, will cause gravitational pull to force water to mound up over on top of it. And we can have a several foot difference between sea heights at the edge of a continent and sea heights in the middle of the ocean. And this is all done through satellite altimetry. So here is South America viewed by satellite, by the satellite altimetry. You can see the high Andes Mountains. You can see the Peru-Chile Trench running the length of the continent on that active west coast. The transform faults and fracture zones in the Chilean rise, that's in the lower left. And you can also see a very large continental shelf on the passive, the trailing edge of the southern part of the continent. So what this tells us is that on the west side of South America, because of that trench, there is a convergent boundary where oceanic lithosphere is subducting under continental lithosphere. But on the east side of, and that makes that an active margin, on the east side of the continent, the continental lithosphere is connected to the oceanic lithosphere. It's acting as one plate moving in the same direction, and we have a passive margin, and there we have a much broader continental shelf. So a cross-section of the Atlantic Basin, we can see this from the cross-section of the Atlantic Basin from C to D, and the cross-section of the United States continent, well, the North American continent from A to B, and you can get an idea of just how big that Atlantic, that mid-ocean ridge is. You can see the Rocky Mountains and the Sierra Mountains. Well, the Atlantic ridge, the mid-Atlantic ridge, that mid-ocean ridge is just about as high as the Rocky Mountains when you do a cross-section. So although ocean depth is definitely greater than the average height of the continent, the general range of the contours are very similar. The general range of the mountain ranges are very similar. So features of Earth's solid surface are shown in percentages of the planet's total surface. So about 10% are mountains, and about 19% are continental lowlands. About 11% of the entire Earth are these continental shelves and slopes, these seaward extensions of the continents. The continental rise, which goes from the shelf down to the deep ocean floor, is only about 4%. And then 30% are ocean basins, about 22% are the ocean ridges, and volcanic island arcs and submarine trenches and volcanoes make up about 4%. So about 70% of the land, or 70% of the globe is ocean, and about 30% is land. All right, here's a graph showing the distribution of elevations and depths on the Earth. So you have on the bottom of the x-axis the percentage of the Earth's surface, and then on the y-axis your depth in meters and your height above sea level. This is not a land to sea profile of the Earth, but rather a plot of the area of the Earth's surface above any given elevation or depth below sea level. So more than half of the Earth's solid surface is at least 3,000 meters, 10,000 feet below sea level. Almost half of the entire surface is below 3,000 feet below sea level. And the average depth of the ocean is about 3,790 meters, which is much, much greater than the average elevation of the continents. What are the two classifications of the ocean floor? You have the continental margins, which we talked about, which are the submerged outer edge of the continents, and then we have the ocean basins. And the ocean basins are the deep sea floor. So the continental margins are still part of the continental crust. The ocean basins are all oceanic crust. So the continental margins will be made of granite, and the ocean basins made of basalt. So what are the two types of continental margins? What makes up the margin? There are passive margins called Atlantic type margins, and they face the edges of diverging tectonic plates, meaning the Atlantic Ocean, the Atlantic coastline of North America and South America look toward a diverging tectonic plate. There is no convergence going on between the Atlantic and the North America. Very little volcanic or earthquake activity is associated with passive margins. And then active margins, known as Pacific type margins, are located near the edges of converging plates. Active margins are the sites of lots and lots of volcanic and earthquake activity. So continental margins, the margins themselves, the seaward extension of the continent that's underwater, has several components. There is the shelf, which you've probably heard about since you were in grade school, the shallow, submerged edge of the continent. And then there's the slope, and the slope is the transition between the continental shelf and the deep ocean floor. The shelf break is the abrupt transition from the continental shelf to the continental slope. And then the continental rise is an accumulation of sediment found right at the base of that continental slope. And that's basically along passive margins, Atlantic type margins. So here's a cross section. So this is the cross section. And what you're looking at here is a passive margins in a deep ocean basin. So here's your continental margin, and here's your other continental margin. And so the continental shelf is the seaward extension of the continent. And it's generally covered by some type of sediment. And that is the continental shelf that goes way out from our side of the continent. And then the continental slope is where the continental crust ends. And it's a downward motion down toward the ocean. And then you get that continental rise, which is more sediment that's flown out into the ocean. Underneath the continental rise is the oceanic crust. So you have this difference between the continent and the oceanic crust. So here's our oceanic crust here, and that's our continental crust. And the two are sutured together, one's not moving toward the other. And this, all underneath this, is going to be your upper mantle, your asthenosphere. Everything underneath these two long red lines I'm drawing is the upper mantle or the asthenosphere. So this is the continental lithosphere and then the oceanic lithosphere. These are two separate plates, one plate and a second plate. And the plate boundary is right here at the ocean ridge. This is a divergent boundary where those two plates are spreading apart. And again, the structure of the ocean basin, both being passive, is your continental shelf, your continental slope, and that takes you from the shelf down to the oceanic crust. And then the continental rise is where sediment has covered that transition. And we have the same thing happening on the other side of the basin as well. So here we are looking at both an active and a passive margin. So your passive margin is here, your active margin is here. Your active margin is active because it is at a plate boundary. That is a plate boundary where an oceanic lithospheric plate is converging with a continental lithospheric plate. Here it's a passive margin because it looks out toward a divergent plate boundary, which is where two oceanic lithospheric plates are diverging from one another at a mid-ocean ridge, in this case the mid-Atlantic ridge. And here this passive margin is where the oceanic and the continental crust are sutured together and moving along on top of the same lithospheric plate. So this is one plate, well, I should say this is one plate, this is your second plate, and over here is your third plate. So why do we have an active margin or a passive margin? So our active margin occurs because it is near this converging plate boundary. Our active margin is where we have a oceanic lithospheric plate subducting under a continental lithospheric plate. We get a trench formation, and this subducting plate creates earthquakes along the subduction zone. And in addition to earthquakes along the subduction zone, the melting of the mantle wedge here creates mantle that bubbles up and eventually creates volcanic mountains along the margin of the continent. So this is an active margin, whereas in the passive margin there's very little volcanic activity, or no volcanic activity. The only volcanism going on or earthquakes going on is out here at the diverging center. So typical continental margin bordering a tectonically active Pacific type and a passive Atlantic type moving continent. The vertical scale, of course, has been exaggerated. Passive margins are continental margins facing the edges of diverging plates, and active margins are continental margins near the edges of converging plates, or near places where plates are slipping past one another. That can also be tectonically active. So those are your passive and your active margins. Now, here's an interesting cutaway of what's happening on the North American plate, up where the Juan de Fuca, which is a small plate, is subducting underneath the North American plate, and that subduction zone creates earthquakes where it subducts underneath and it basically rubs against, the two plates rub against each other. And then the mantle wedge that melts creates our active volcanoes. So Mount Rainier, Mount Adams, of course, this is where Mount St. Helens occurred as well. So this is a very good example of an active margin, an active continental margin where a subduction zone is creating a lot of earthquakes and a lot of volcanism, a lot of volcanoes. So I said our continental shelves and our continental margins are really seaward extensions of the continents. Most of the material composing a shelf comes from the erosion of the adjacent continent. So here's our adjacent continent, and most of this material is all some type of sediment. Rivers transport most of the sediment that makes up the continental shelf. The continental slope is a transition between the continental shelf and the deep ocean floor, and turbidity currents are just basically currents of water that are denser because they're full of sediment, transport most of the sediment that makes up the continental rise. And again, this is our continental rise between the continental slope here and the deep ocean floor. So the oceanic crust probably extends to about this point. Everything west of that is going to be continental crust. This is all oceanic crust. And the continental rise literally covers up that transition zone. The continental slope is the transition between the oceanic and the continent, and then the continental shelf is largely covered in sediment as well. One of the things that we know by looking at geology and ice cores and sediment cores is that the climate of the Earth has changed almost continuously over the 4.6 billion years the Earth has been around. This is a graph showing about 250,000 years. And on the far right, that point C is today's sea level. And what this graph is showing us is how sea level has changed, and dramatically at times, over the last 250,000 years. And this data is taken from ocean floor cores, and those ocean floor cores give us a very good idea of the temperature at the time, and knowing the temperature gives us an idea of how much of the ocean water is locked up in the ice during the ice ages. So the rise and fall of sea level is largely due to the coming and going of ice ages, periods of increased and decreased glaciation. Literally, when you have large glaciers during an ice age, tremendous amounts of glaciation over the continents and the oceans, the water is locked up in the ice and the sea level falls. So colder periods create lower sea levels. Point A indicates a low stand about 125 meters at the climax of the last ice age. So the end of the last ice age is right here is thought to have ended anywhere between 12 and 18,000 years ago. And that was when we were very, very cold. The ice age began to end, and immediately temperatures began to rise, and sea level also began to rise. And the thinking is, based on observations, is sea level continues to rise at this point. Now, B indicates a high stand, 6 meters or so above current sea level during the last time we were interglacial or between glaciation. So this cold period, low sea level, represents glaciation. This cold period, low sea level, represents glaciation. This is the last interglacial. We're currently in an interglacial as well. And that was about 120,000 years ago, the last interglacial. And point C shows the present sea level. So sea level continues to rise as we come out of the last ice age. And because we are entering this period of global warming, it appears as though sea level increases are accelerating as well. All right, a little bit about submarine canyons. They're features of some continental margins. You have to have water coming off the continent to have a submarine canyon. They cut into the continental shelf and slope, and they basically terminate with these deep sea fans out on the deep sea floor. And this avalanche is one of those turbidity currents that I was talking about. This is actually a picture taken just offshore of Jamaica, and there was a submarine in port, or close to port, that was very close to the bottom, and its propellers kicked up enough sand off the bottom, sand and silt and whatever sediment was on the bottom, that it kicked up this big cloud of silt. And because that cloud had more stuff in it, it was denser, that water was denser, and that dense water literally rolled downhill. So An avalanche-like sediment movement caused when turbulence mixes sediments into water above a slope. They're called turbidity currents. The turbidity current flowing down a submerged slope off the island of Jamaica. Here again, the propeller of a submarine caused the turbidity current by disturbing the sediment along that slope. All right, so we've talked a lot about the continental margins, the continental slopes, and the rises, and now we want to talk a little bit about the deep ocean basins. So the features of the deep ocean basins, we talked with plate tectonics about the oceanic ridges. There's also the abyssal plain between the ridge and the continents, and abyssal hills. And then in addition to that, there are seamounts and volcanoes, and these things called guyots. There's trenches and island arcs, and there's hydrothermal vents. All right, so this is an illustration of all the oceanic ridges, and this is where continents have been spreading apart and oceans have formed as those rift valleys got bigger and bigger and bigger. So this is the Atlantic, Mid-Atlantic Ridge, and then the Indian Ridge, and that crosses over here down into the Pacific Antarctic Ridge. And the East Pacific Ridge is displaced because there's been almost continuous spreading for almost 225 million years here. And then this East Pacific Ridge sort of culminates here where we have some subduction, and then we also have some transform boundaries. And so this is where our spreading ridges are. So an oceanic ridge is a mountainous change of young basaltic rock at an active spreading center of the ocean. If the ocean evaporates, the ridges would be Earth's most prominent feature. Ocean ridges are widest, fastest spreading rates where they're most active, like in the Pacific. So really rapidly spreading in the Pacific, and so that's where they are the biggest. Upwelling of magma from beneath the ocean floor causes the ridges to bulge up. They are often devoid of any sediment because they're the youngest rocks on the ocean floor, and those youngest rocks are always located at the active ridge center. Again, because the Earth is a sphere, we can't have one continuous line of a spreading center. So these spreading centers get split and displaced from one another by these transform faults. The transform faults and these fracture zones along oceanic ridges. Transform faults are the fractures along the lithospheric plates as they slide horizontally past one another. These plates in the fracture zone are moving in the same direction, while the transform fault, they're moving in opposite directions. So it means that these two chunks of the plate are moving in the same direction, and these two chunks of the plate are moving in the same direction, but at this transform fault, the plates are moving in opposite directions. Now, here the plates are moving in opposite directions, and that's a fault. In this location, these plates may be moving in the same direction, but they could also be moving at different rates. And so that's your fracture zone, and that's your transform fault. All right, hydrothermal vents, very, very interesting. They are sites where superheated water containing dissolved minerals and gases escape through fissures or vents. So cool water, shown by the blue arrows, is heated as it descends toward the hot magma chamber. So in this period of this water moving through this rock, it leaches out, or it takes out the sulfur, the iron, the copper, the zinc, and other materials from the rock. Then as that water is heated, it becomes less dense and it bubbles up through the mid-ocean ridge, returning to the surface, carrying those elements upward and discharging them at the hydrothermal springs or the hydrothermal vents. So those hydrothermal vents right here in the center of that mid-ocean ridge are hot springs on active oceanic ridges. So this is the cross-section of the very central part of the mid-ocean ridge. And what you have to remember in this mid-ocean ridge situation is the entire mid-ocean ridge looks something like this. It's a ridge, and then you get this central rift valley. And so the ridge is this very long point across the entire screen here, all right? This section on this illustration from here to here is just being shown right in this section on what I've drawn. So this on the illustration is just this very central section. The ridge is significantly higher than the rest of the sea floor. All right, so a cross-section of the central part of the mid-ocean ridge showing the origin of those hydrothermal vents. water leaches down through the oceanic crust, picking up all those minerals, and where it's superheated, it bubbles back up. And sometimes they call these things black smokers or white smokers, depending on the type of chemicals that come out. But in addition to these hydrothermal vents, this zone is also where any new magma would bubble up and form and create new rock, causing those ocean centers, again, to move away from each other. So this is literally the point of a plate boundary, a diverging plate boundary, right up to the center, of this. And not only do you get these hot smokers, but this is also where you get magma and volcanic activity as well, where that magma flows out, creating lava on the sea floor that solidifies into rock. Some other interesting features on the sea floor are these seamounts and guyots. Seamounts are the volcanic projections from the ocean floor that do not rise above sea level. So a seamount is going to be anything that doesn't quite ever get to sea level. And very likely they are formed at the mid-ocean ridge, and then they are carried away from the mid-ocean ridge as those two oceanic plates diverge. All right, well, if they can get to the surface, much like they did in Iceland, then you have volcanoes above the surface. If they don't get to the surface, they're called a seamount. Where you get a guyot is where you get this volcano that rises above the surface, and then as it begins to move away, it's no longer forming, and the sea surface literally erodes away the top of it, so it becomes flat. And then as it continues to move away, it just becomes this flat-topped seamount. So a seamount is not flat-topped, and a guyot is flat-topped. Abyssal hills are flat areas of sediment-covered ocean floor found between the continental margin and the ocean ridges. Abyssal hills tend to be quite small, extinct volcanoes or rock intrusions near oceanic ridges. Due to the accumulation of sediment, though, abyssal plains, the plains way out here, are very, very flat. Most of the sediment is of terrestrial or shallow water origin, meaning all the sediment that covers the abyssal plains is basically coming off of the continents around the ocean. All right, the other thing that tectonics does is where we have converging plates, whether it's oceanic and oceanic, oceanic and continental, those two converging plates are going to create trenches. Trenches are arc-shaped depressions in the ocean floor caused by the subduction of converging ocean plates. Trenches and their associated island arcs form in subduction zones. Most trenches are around the edges of the active Pacific, and the trenches in the island arcs are among the most active geologic features on Earth. If you think about all the earthquakes and volcanoes in Japan lately, that's because you have a very significant plate motion here and a significant oceanic trench. Trenches are the deepest places on Earth, and there's between 3 and 6 kilometers deep. The deepest, much deeper than the adjacent basin floor. The ocean's greatest depth is the Marianas Trench. The deepest reaches more than 11,000 or 36,000 feet below sea level, and that's the Mariana Trench right there, and there's the Challenger Deep Trench. So those are the deepest trenches. And literally, this is where two oceanic plates are converging. And when those oceanic plates converge, so here's one, that's the younger and the less dense, and here's the older and the more dense because it's colder. There is the oceanic trench, and with these very fast subduction zones, you get these very deep trenches, and that's where our ocean trenches come from. So there's the Mariana Trench and the Challenger Trench. Actually, deeper than Mount Everest is high, and I guess that's the point. About 20% deeper than Mount Everest is high. All right, so that's kind of our look at ocean basins. It was very difficult to discover the shape of the seabed. Using a weight at the end of a rope was not a good method at all. But then with the development of echo sounders and then submersibles and then multiple beam echo sounders, we were able to get a better handle on the shape of the ocean floor. But even today, it's thought that we know more about the contours of Mars than the contours of our own ocean floor. So we know that the seafloor feature results from a combination of tectonic activities and the process of erosion and deposition. So think about that. A lot of what we talked about was a function of plate tectonics creating trenches and ridges. But the reason why the continental shelf or the continental rise exists is because of erosion from the continent and the deposition of that sediment on the ocean floor. And the reason why the abyssal plains are flat is because millions of years of sediment have filtered down and just flattened out on top of the seafloor. So the ocean basin is a combination of tectonic activity and the processes of erosion and deposition. The ocean floor can be divided into two regions: the margins, which are the seaward extensions of the continents, and the deep ocean basins. The continental margin is relatively shallow ocean floor nearest the shore, consists of the continental shelf covered by sediment and the continental slope. And remember, the continental rise is that sediment that connects the slope and the shelf together. Continental margins share the structure of the adjacent continents, but the ocean floor away from the land has a much different origin and history. Prominent features of the deep ocean basin include the oceanic ridges, flat abyssal plains, deep ocean trenches, curving chains of volcanic islands, and it's the processes of plate tectonics, erosion, and sediment deposition that have shaped the continental margins and our basins. All right, that is a look at Chapter 4. We'll be back again with Introduction to Oceanography, Chapter 5, next time.